Welcome to my seminar about non-rocket launch systems. But before talking about alternatives for rockets, I want to talk about rockets, what they are good at, what they are bad at, and how we might be able to replace them. In order to transport the narrative, here we can see a standard Kerbal Space Program rocket with a satellite which is transported into Kerbin orbit. We do this all the time on Earth. For space engineering, this is everyday business. We build our satellite or payload, put it on a rocket, then we launch it. We have no other possibility than putting it on a rocket. Yes, there are systems which use a plane to somewhat replace the first stage, but in the end it is still a rocket boosting up most of the height, putting in most of the energy to raise the satellite. Now, generally speaking, there's of course nothing wrong with that. Our rockets work, they are sophisticated. We had thousands and thousands of launches. We know how to do it. But is it really the way to go? If we look into the industry, the answer might be no. SpaceX is working on rockets which are reusable. So reusability in launches is an important thing. Well, SpaceX is able to land rockets, yes, but there are alternatives out there which do not rely on rockets and can be reused and can launch satellites. And such alternatives are what I want to introduce to you today. So to compile the information, rockets are sophisticated. Their source of energy is fuel. Will it be solid fuel or cryogenic fuel or two-component fuel or something hypergolic is not important. The problems are they are hard to reuse. Yes, some companies are doing it, but it's really hard. And compared to what we will see, the masses they can transport at once are relatively small, especially compared to the amount of energy and resources which need to be invested just to raise, say, 1 kilogram. The first group of non-rocket launch systems I want to introduce to you are a subgroup of linear mass accelerators, the most sophisticated one, the so-called electromagnetic or EM railgun. The most sophisticated mass accelerator is the railgun. It is mostly used in weaponry, and we will later see a video of a US Navy test of a railgun. But here we can see how it works. Current flows through two rails. The projectile connects those rails, and the magnetic field induced by the current is forcing the projectile to the front. Now the premise is that some part of the projectile is magnetic, otherwise this doesn't work. This can create huge forces and huge speeds, which we will see in the following video. Here we can see the air lighting up. There are no explosives involved, it's the projectile turning the air into plasma. The projectile is traveling at Mach 7, which is somewhat the speed which is needed for orbital injection, more or less. Well, this is a gun and the projectile is rather small, but the technology is being worked on, and that's the important thing. Also, the technology has been researched as a launch option. And now we will discuss which parameters an orbital railgun would need to have. Ian McNabb in one paper suggests that you should build a railgun on the side of a mountain, having your own power plant, and of course build it as close to the equator as possible, as this gives a lot of more possibilities for azimuth and helps with the launch velocity. The reason for the suggested height is to skip as much atmosphere as possible, as the exit velocity at the muzzle will be the velocity you get. There will be no further acceleration. and to drop as much air resistance as possible, the height which has been suggested is beneficial. A company called Quick Launch went with a very different approach. They designed a water-based, or more like sea-based, Railgun Launcher. The advantages of this launcher is that it is movable. It can not only launch from anywhere in the world where there is sea, but it can also change its inclination, which the mountain-based launcher can't. Another advantage is that it is also water-cooled, which is important because the electromagnets generate a lot of heat. Disadvantages, of course, are that it is hard to maintain because you need divers to check the tube and maintain it, and another disadvantage is that you launch from sea level, so you have more atmosphere to go through and you have more atmospheric drag. Of course, it needs to have a distinct launch vehicle, and the very basic components are shown here. Especially interesting is the nose, because it needs to withstand really immense amount of heat due to the aerodynamic drag. Also still needed is a rocket motor, a rather small one, just to circularize the orbit, because just a railgun cannot achieve an 100% orbital injection, because the perigee will always be around the surface of the Earth. The payload is in the middle, and for docking, of course, there also needs to be some kind of rocket motor. This part of the launcher is not reusable, but of course the tube, the railgun, is reusable and needs, compared to a normal rocket, basically no refurbishment at all, which is a big advantage. So to conclude, we have also a picture of a railgun built on the moon, because this can also be a possibility, and aerodynamic drag then is not a problem. I want to show you what the parameters of the railgun are. It is very reusable. It uses electric power, which is an advantage because we can generate that however we want, be it solar electricity, be it any other source. The disadvantages are the high heat, which demand for a special launch vehicle. The bad options for inclination, because yes, there are ideas of how to launch these or turn these launchers, but they are massive and turning something like this is not that easy. And since the acceleration is so high, within a few kilometers from 0 to multiple kilometers per second, which means over 100 G, human transport is not possible with those mass accelerators. Another launch option, which employs some of the advantages of the railgun and adds some advantages, for instance, easy choice of inclination, are the Slingshot or also Slingertron launchers. One of the companies actually developing a launch system based on the principle of a slingshot or a Slingertron is Spin Launch. Spin Launch came out of silent mode in 2018, more specifically in March of 2018. The only picture available so far is the scene rendering, where, as already described in the section about EM railguns, a small launch vehicle is needed, and it then is put into the launcher for launching purposes. Spin Launch got funding from Airbus and Google of a contract of $40 million, and therefore is on a good track to actually develop the first prototype of a slingshot launcher. Spin Launch has been very vague on which technology they want to use, as there are different approaches to spin launching, but I want to introduce some of them. The basic principle of the circular launch track is that angular velocity wants to be transformed into linear velocity, which is then used for the launch. And this can be done in either of two ways. You either change the radius of the launch track and keep the oscillation, so omega, constant, then you have a spiral launch track. Or you keep r constant and change the angular velocity. Therefore, you would have a circular launch track. You could of course also change both, but that would be more complex and usually is never considered when thinking about circular launch tracks. There's no chemical or electrical propulsion involved, it's purely mechanical. It's by means of momentum exchange. Imagine you're holding a circular tube, and within the tube there is a ball. If you start swinging or nutating the tube at just the right speed, the ball will start moving, and that happens due to momentum exchange. And that's how these launch tracks, either circular or spiral, work. So I want to explain both launch tracks. First of all, the spiral launch track. It has the advantage, as mentioned earlier, that only the radius changes but not the gyration sense, the angular velocity. This is very favorable since these launch tracks have multiple hundreds of meters in diameter and are hard to rotate anyways, so if the rotation is at least constant, it helps a lot with the technology. So in the zoomed in view we see the forces which act upon the projectile. The centrifugal force induces a friction, and the friction needs to be overcome by the push force. The push force is the momentum exchange I mentioned earlier. The push force, as you can see, also induces a slight sideways velocity, but that can be neglected because the walls of the launch track are taking these forces and are stabilizing the vehicle. So when we can overcome the friction with its push force, the vehicle will accelerate, and when the track is large enough, it will reach orbital velocity. Here we have an animation showing again that the whole launch track oscillates. The vehicle is released, it's accelerating, and then leaves the tube with orbital velocity. Now on to the circular launch track. The radius of the circular launch track is constant. Therefore, the oscillating speed needs to increase. As I said, the radii of these launch tracks is multiple hundred meters, and oscillating something like this is not easy, and it doesn't get easier when the oscillation has to be faster and faster. But there's an advantage of the circular launch track. The inclination angle can be freely chosen, whereas with the spiral launch track it can't. You just need to put an exit, which is here shown on the bottom left, at the right position and release the vehicle at the right time. So what can we conclude about Slingertrons and Slingshot launchers? They offer, in terms of inclination or azimuth angle, a very good opportunity and alternative to EM railguns. One can, especially with the Slingshot, decide which inclination he wants to have. It's also using electric energy. Well, it can be using other types of energy, but electric energy is a possibility, and that is a big plus. A negative are the high centrifugal forces, and those forces can be up to 100, 200, 300 Gs, depending on the radius of the launch track and the speed. But this is not the problem. There have been electronic devices which have to withstand those forces. For instance, artillery shells. They have electronics built into them, and within the muzzle they see forces of over 1000 G. Also from our University of Würzburg, UWSAT 1, was tested to withstand up to 10,000 G, which is way higher than what is expected in the Slingertron. The last contrapoint is that some of these launch tracks require to spin the whole launcher, in fact. It has not been mentioned, but circular launch tracks can also be made by just circularizing an EM railgun, but since that principle is so trivial, it shall be mentioned now and no further explanation will be needed. But For the specialized circular launch tracks and spiral launch tracks, this of course is a disadvantage. And with that we shall conclude with Slingertrons and Slingshot launchers. And last but not least, some honorable mentions, so to say. There are many more non-rocket launch opportunities. If you're very interested in them, I suggest to you reading the book Non-Rocket Space Launch by Alexander Bolonkin. Here I want to mention the most discussed ones, which are either really built or highly theoretical, but on the verge of being maybe built. The first one is the space elevator. The space elevator has a separate seminar topic to it, so I won't go into detail with it. The second launcher in the middle depicted is the so-called Kite Launcher. An airplane carries on a tether the projectile, so to say, the spacecraft. The aircraft, kind of like an Olympic hammer thrower, flies in circles and acts as the counterweight for the spacecraft. And the faster the airplane goes, the faster the angular velocity and the faster the speed of the spacecraft. The spacecraft then, when it has reached the desired velocity, can be released from the tether and go into space. Well, you can imagine this process is quite violent on the aircraft, and this is the main reason why it has not been tested so far. On the top right, that's the orbital ring. The orbital ring is a combination of multiple technologies. First of all, the space elevator, which brings the payload into geostationary orbit, and then a way of magnetic train, maybe a coil gun or railgun, can do the job. So it has the means of what we already explained, but the final orbital speed is reached in the ring. The big advantage of this is that with a space elevator humans can be transported. With the other technologies we presented today they cannot, because of the high accelerations. So this hybrid system would allow us to launch payload and humans with the same technology. The big disadvantage is, of course, it demands for a ring the size or the diameter of the geostationary orbit, which is within the next 20 to 30 years or maybe 100 years. Very unlikely. And the last technology is an advanced linear mass accelerator like a EM railgun or coil gun. Here, the launch track accelerates the vehicle like explained earlier, but it also goes to a height of 80 kilometers, releasing the vehicle in an environment where drag is almost zero or very much neglectable for a space launch. That sounds very good, but how would one levitate the launch track in the height of 80 kilometers is the question, which cannot be answered today. And before we can tackle the advanced EM railgun, we need to master the EM railgun. Which brings me to the conclusion of this video. Non-rocket launch systems. It's not a new idea. Here on the right you can see a sketch of an old space gun from 1886. It is being developed. Companies like Spin Launch work on it. The US Navy works on it, well, as a gun, but if the gun technology is developed, it can also be used as a launcher. And last but not least, it is possible. Otherwise companies like Airbus and Google wouldn't spend as much money, millions and millions, on it. So lifting tons and tons of material into space is easy with those launchers. They are easy refurbishable. There is no need to refuel. Those are electric launchers. they can launch within minutes after another. It can be so fast. Material can be launched so efficiently. The only downside? It's not for humans. Humans would not be able to withstand the huge forces, as we have seen multiple hundred Gs. But this doesn't matter. Rockets can still provide for human launches. And space elevators can too. But as I said, that's the topic of another seminar. So one can look with excitement into the future. We might be able to launch our satellites without rockets soon. And this can bring a whole lot of new possibilities.